Okay, so today's class we are looking at topic 4, which is called the energy connection. So first of all, what is energy? So we've talked about this a little bit before. Energy is the ability to do work, and energy appears in many forms. For example, electric motors. They use electric energy to do work on objects by moving them. Electrical devices like light bulbs and stoves. They change electrical energy into light and heat. Other technology can transform heat, light, and energy of movement into electrical energy. So that's what we'll look at today. Here in this diagram, we just have heating elements that are able to convert electrical energy into thermal energy. Also keep in mind, kinetic energy is the energy of motion or movement, whereas potential energy is stored energy. So firstly, we'll look at electricity and heat. So lots of different appliances like stoves, the hair dryer, ovens, and so on. Electric energy is being converted to heat as moving charges meet the resistance of a metal conductor. So a device called a thermocouple is where heat can be converted directly to electrical energy. So in a thermocouple, there is usually a loop of two wires that are made up of two different types of metals, and they are wrapped together at both ends. And then one end is heated. It's also called a junction. A small electric current is produced. And then if there's a temperature difference between the junctions, and if it's increased, the current increases. So for example, one junction might be cooled, the other side might be heated. And again, if you reverse that, if the positions of the hot and cold junctions are reversed, the current will flow in the opposite direction. So not every combination of metals will work. Usually copper and constantan, that's a copper-nickel alloy, will work. Iron and constantan is another combination. They're the most common metals that are used in modern industrial thermocouples. All right, so here's just a diagram showing the thermocouple. So they are used to measure high temperatures. They're also used as sensors in safety and control devices, in furnaces, in hot water heaters, and electric ovens as well. Next, this is a thermoelectric generator. So this is a device based on a thermocouple. It'll convert heat directly into electricity without any moving parts. So heat from a gas burner or another heat source, it'll move through several thermocouples connected in series. That's called a thermopile. It'll create a potential difference. They are very reliable. They're low maintenance. They are used in remote locations to generate limited quantities of electrical energy that are sufficient to power like emergency communication equipment. So heat flow through the thermopile, it will create a steady flow of electricity. And the output ranges from 15 to 550 watts, and they can be combined to produce up to 5,000 watts. Okay, so next, the 4 common forms of energy. So chemical energy, that's the energy stored in chemicals. It's a form of potential energy or stored energy, and then it gets released when chemicals react. So think about like the food we eat, that would contain chemical energy. Gas, the gas to like start a car, and so on. Like those would have chemical potential energy. Electrical energy, that's the energy of charged particles. So electrons, those are negatively charged. So electrical energy is transferred when electrons travel from place to place. Mechanical energy is based on motion or its potential to move. So for example, if you throw a baseball, that would have mechanical energy because of its movement and the potential to fall. And then thermal energy, that's the total kinetic energy of all the particles in a substance. So, like if you increase heat, particles move faster. So the faster a particle moves, the more kinetic energy it has. Like if you compare 2 cups holding equal amount of water, the one that has more thermal energy will feel warmer. All right, so we'll just pause here and focus on the forms of energy. So chemical energy, this is the energy that is found in chemicals. It's included in the food that we eat. When we eat and digest the food, that gives us energy. A common molecule used for the production of energy in humans is glucose. It's a type of sugar. So here we can see a glucose molecule made of like carbon, hydrogen, and oxygen. So our cells use glucose, and then there's a series of reactions that occur to produce thermal energy, which keeps us warm, and mechanical energy so that we can move. Chemical energy can be transformed to other forms of energy as well, like when you use batteries, something battery operated. The chemical energy is being transformed into other forms. Explosives, those are also chemicals. For example, here to break a building down. Okay, so it's the chemical energy from the explosives, which will then transfer as mechanical energy for demolition and so on. Yeah, so the building itself would also have gravitational potential energy, and then the collapse of that will then release energy as sound and heat and so on. Okay, transformations involving chemical and electrical energy. So these are some devices that convert energy from one form to another. So for example, a toaster converts electrical energy to thermal energy. So the input is electrical, the output is thermal. A flashlight are battery powered, so chemical energy is the input, the output would be light, but thermal as well, because there is waste heat. A blender, input energy would be electrical, output energy is mechanical. A battery operated clock, input energy is chemical, and then output energy is electrical, mechanical, and sound. Those are just some examples. This next part is called electricity to motion. So there is sound produced when an electric current causes vibrations in a tiny crystal. And this is called the piezoelectric effect. Piezo in Greek means pressure or push. So there are crystals that have this effect. So when a piezoelectric crystal, such as quartz or Rochelle salt, when it is connected to a potential difference, the crystal will expand or contract slightly. And then any material touching the crystal experiences pressure, which then creates sound waves or vibrations. So researchers, they've developed non-crystalline materials that move in response to an electric current. For example, a flexible polymer, which is a plastic, was used to create a robotic hand with 4 fingers. And when voltage was applied, those plastic fingers were able to bend and were able to grip small objects between them. All right, so an electrical signal here, and then we have some sort of material here, like a piezoelectric crystal. And then, so that was electricity to motion. And then we can take motion to electricity. So for example, barbecue lighters that look like this, they use the piezoelectric effect, but in reverse. So a piezoelectric crystal, it's being compressed or pulled, a potential difference builds up on opposite sides of the crystal. There are conductors attached to the crystal that connect it to a circuit, and then that crystal acts as a source of electric energy, and it creates a spark in a barbecue lighter. Other devices like crystal microphones, some pressure sensors, they use the changing voltage from a piezoelectric crystal to control much larger electric currents, for example, in amplifiers and recording equipment. Okay, so again, barbecue lighter, when you squeeze the handle, it slams a tiny hammer against a piezoelectric crystal. It'll generate a potential difference, and a potential difference is generated of thousands of volts, and a miniature lightning bolt across the spark gap. I'm just going to move ahead here, and we'll watch this video on the piezoelectric effect, and then we'll go back. So the next topic we're going to talk about is electricity to light. So light bulbs, like incandescent light bulbs, they contain a filament inside of them that's made of a high resistance metal, and that metal will glow brightly when an electric current passes through it. And then we also talked about fluorescent and neon bulbs. In those types of bulbs, an electric current is passing through a gas or vapor to glow brightly. Piezoelectric crystals, they can also produce light when they are hit together. We saw that last class. And then lastly, there's light emitting diodes. These are LEDs. So you'll see some of these LEDs, you'll see them in like flashlights, bicycle lights, some toy lights. They don't have a light bulb, they have this light emitting diode, so these LEDs. So they are solid state electronic components. They will glow when electricity flows through them. And the pro or the advantage of using LEDs is that they use only a fraction of the power of a traditional bulb, and they can last for years as opposed to just months. So the heart of the LED, it's a tiny semiconductor chip, and it's often protected by a transparent plastic case, and they will work when connected to a circuit, but only in one direction. So here we can just see a comparison of a standard incandescent bulb, a compact fluorescent bulb, and then an LED. So you can see the watts, the lumens. Look at the life in years, 0.9 for standard incandescent, 9.1 years, and then an LED, 22 years. For energy cost, it's also very low. If you look at an LED, it's only $1.56, and the initial cost though is high. So if you look at the initial cost of the bulb, it is higher, but you are saving money in the long run when you look at the annual energy cost. All right, these were the ones we had just watched last class. Okay, and then light to electricity. So we're looking at solar power cells. So, for example, the International Space Station, it is powered entirely by solar arrays, electricity generating solar arrays. So the most common device that's used to produce electricity from light, it's called a solar cell or a photovoltaic cell, a PV cell. So they're made of semiconducting materials like silicon, and what happens is when light strikes the cell, some of the light gets absorbed by the semiconductor material. Electrons will break loose and allow them to start flowing freely. There are metal contacts on the top and bottom of the PV cell. That's what is allowing the electric current to be drawn off for external use. Then you can use them in devices like calculators, water heaters, emergency roadside telephones. An individual cell, so if you're just using one solar cell, the energy is limited. Voltage and current are limited. So solar cells will usually be combined to form modules, and then they are can then combine to form arrays. Here is an example. This is a rooftop solar array, and it can be used to power a house. We'll take a look at a couple videos here. How do solar panels work? So I'll just pause here. All right, so next we're just talking about some organisms that can produce electricity. So many fish, electric eels, can use, they have these organs, electric organs within their body, and we'll take a look at a video as well that will show this. They'll use these electric organs for a variety of functions like detecting enemies, to navigate, and possibly to communicate as well. So these animals, they're said to be electrogenic and electroreceptive. So this is the South American freshwater eel, and it's able to generate the largest voltage of any fish. So there's this electric organ here, and it has thousands of flat specialized muscle cells that are called electroplaques, and they make up about 40% of the eel's mass, and each cell can generate a voltage of about 0.15 volts. The cells are connected in series, so the electric organ, it can generate a total voltage of about 600 volts. So it can use this to stun its prey. An electric shock causes the prey to stop breathing and drown, and then the eel can consume its meal. All right, so we'll watch a couple videos here. I'm going to pause it here.